It's my pleasure to introduce the next speaker of our seminar. It's Yaroslav Bazaikin from the University of Ústí nad Labem, who will talk about Chern-Losik class for codimension 2 foliations. So please.
Okay, thank you. First of all, I would like to thank Svan for inviting me for this talk. And okay, I will speak about Chern-Losik class in codimension 2, about some new examples. Okay. Okay, I will use maybe. Doesn't work. Okay, I can use mouse. Yeah. So I will speak about foliations. So it's usually foliation is some partition of manifold and dimensional manifold into leaves, and locally leaves looks like direct product of some Euclidean RK, and n minus k is a codimension of foliation. And this is, of course, is a generalization of fiber bundle. And okay, now it works. And consider, we will need the notion of holonomy of foliation. Let's fix some leaf L alpha 0, some point in this leaf, and consider the loop which start in this point and end in the point P. And then we can consider transversal U. You can choose any transversal, and then any point Q can be transported along this curve. So using these local maps of foliation. And so we will have some diffeomorphism, and this diffeomorphism will be only local diffeomorphism on the transversal. And all such diffeomorphism over all gamma will be the pseudo group. This is not group because every diffeomorphism is defined only locally. And this is holonomy group. And first of all, I would like to remind the concept of Chern-Losik, concept of characteristic classes for codimension 1. So in codimension 1, let we have transversal. Transversal is one-dimensional. Okay, sorry. One-dimensional. And we consider space of all jets of order less or equal than 2. So S2 of U, in fact, is diffeomorphic to U cross R cross R. U is the transversal, and we have two coordinates, x1 and x2. So for any smooth map F from R to U, x1 is a logarithm of first derivative, and x2 is second derivative divided by f prime squared. Okay. Okay. Later it will be clear why we need this f prime minus 2. And now, if we have some local diffeomorphism from U to V, for example, U and V are two transversal in foliation, then we can lift this diffeomorphism to the jet space from S to U, S to V, and we have the following transformation of coordinates. So here, x0, x1, x2 coordinates in U, and alpha 0, alpha 1, alpha 2 corresponding coordinates in V. And then we have the following invariant 3 form: d alpha 0, d alpha 1, d alpha 2, and dx0, dx1, dx2 is the same form in different coordinates. So we have invariance of this form, and this gives the first characteristic class, got beyond very Losik class. This class, okay, this is not correct, not H2, but H3 of S2 MF. And what is known about this class? Let's consider RIP foliation. Okay, RIP foliation, in fact, it's not unique foliation, but this foliation depends of some function. This function describes the asymptotics of non-compact leaves when they converge to compact leaf. And so we have in the center of this construction, we have some function with one fixed point, and which is infinitely tangent to identity map. So this is function phi. And moreover, these diffeomorphisms can be included in one parameter group of diffeomorphisms phi t. And this one parameter group is generated by some vector field. So this is called Zekers field. So in other words, we can define, we can construct RIP foliation using some vector field. So any vector field gives some RIP foliation. And what we have, consider the following vector field. This is this vector field depends of alpha. Alpha is an arbitrary number, and what is known that if alpha is a natural number and odd, then okay, I skipped. God beyond V class is not zero, and for even alpha, this God beyond V class is zero. And moreover, we can take two RIP foliation, and because two solid torus, if you glue two solid torus over the compact torus, we can get three-dimensional sphere. And so we have foliation in three-dimensional sphere. And we proved also with Anton Galaev and Pavel Gumenyuk that if alpha is odd and beta is even, then these foliations are not diffeomorphic. Okay, and so this is about RIP foliation. So we see that different parameters of asymptotic of non-compact leaves gives different topology of foliation. And now consider the Chern-Losik class. For this, we need to associate with S2 of u. S2 of u is a jet space. We need to associate factor space. So we factorized S2u by GL1. GL1 acts by multiplication to the coordinate x1. And from this action, it's clear why we need special coordinates. So in these coordinates, we see that x2 A is not, it doesn't act on x2 and x0. And so after factorization, we have only two coordinates, x0 and x2. And we have new invariant form, x2, x0. So again, this form is invariant. And we get Chern-Losik class, first Chern-Losik class, the Cohomology class of this form. And it was proved by us, me and Anton, that for RIP foliation, Chern-Losik class is not zero for any function f, for any vector field. Yes, so this is yes. And in fact, Chern-Losik class first was constructed by Losik, and I would like to say several words about Losik examples because it's very geometric. It was the first example when it was proved that this class is non-trivial. And what is this? We need to consider some diffeomorphism of circle with two hyperbolic fixed points, P and Q. Hyperbolic means that we have non-unit derivative in this point. So f prime p not equal to 1 and minus 1, and f prime q also not equal to 1 minus 1. And first of all, Losik proved that if we lift this diffeomorphism to the jets, then on the jets, we also have some fixed point over these points P and Q. So for P tilde, Q tilde. And then there is a very geometric construction. In fact, I can, so if we have circle, we have this point P and Q. On this, over these points, we in fact can find also fixed point P tilde, Q tilde. Then Losik consider arbitrary curve, gamma of t, and consider the image of this curve under the f tilde of gamma of t. And then he considered the disk with boundary consisted of these two curves. Then if we now consider all this in the space of jets S1 over phi and psi by phi, then this is a cycle and a two-dimensional cycle, and integrating Chern-Losik class over this cycle, we get this formula. So we can see that if derivatives of f in point P and Q are not equal, then this is not zero. And so this class is non-trivial. So this was the first example of non-trivial Chern-Losik class. And okay. And now I consider construction of Chern-Losik class for codimension 2. For this, okay, so I will speak about some concrete examples, but construction is very general. So in fact, if we have foliation of codimension 2, then we can speak about two-dimensional transversal. And holonomy group acts on this transversal by some diffeomorphisms F. And in fact, we need to construct classes which belong to this group. So we need to consider jets over D factorized by F with respect to GL2. So this is a direct generalization of this class. And I will consider all example in the following way. This is suspension foliation of some diffeomorphism disk to disk. So we need to consider the product of this disk by unit segment from 0 to 1, and then identify these disks by F. So we need to identify F of, for example, X by F of X. And this gives one-dimensional foliation on solid torus. And okay, and we will study the classes of this foliation. Okay, and how to define Chern-Losik class in this situation? So now we need to consider space of jets of maps F from R2 to D. And so we have the following coordinates. First of all, two coordinates Z1, Z2. This is simply the zero orders jets. So FE00. Then we have coordinates zij, dfi, dtj in point 0, 0. So this is the jets of first order, and the jets of second order, all second derivatives. So in fact, the number of coordinates much bigger than in previous case. And we transform these standard coordinates to the new ones. So yi equals zi is the same, jets of zero order. First order jets also the same, but second order jets we multiply by inverse matrix with respect to first order jets. So we have this formula and new coordinates. And then after this transformation, we have action of the group GL2 on space of all jets when matrix acts only on first order jets. This is a direct analogy with respect to previous case of codimension 1. And after factorization, we have only coordinates yi and yijk. So these 0 and 2 order jets generate coordinates in this space. So S2D factorized by GL2R. Okay, and we denote this again by S2 prime of D. So this is coordinates, and if these coordinates, if we take these coordinates, and again consider, for example, two transversal, D and U is some another transversal, and G is a diffeomorphism from holonomy group, local diffeomorphism. We again can lift this diffeomorphism to the space of jets, and we have the following transformation of coordinates. So now Y is coordinates in D, and eta coordinates in U. So we have this transformation. And what is important is that we can associate some shorted coordinates. So yi below index, I mean summation over index j. And after that, we have this form, which is invariant with respect to diffeomorphism. We see that this is some generalization of first Chern-Losik class for codimension 1. For codimension 1, we have only one term, dy1 below, dy1 upper index. So, and we have this invariant form, and we call this first Chern-Losik class for codimension 2 foliations. And in fact, all this construction can be also used in any codimension. For example, if you look at these formulas in fact valid also for any codimension, not only for 2. And in this case, we have form with n terms, where n is codimension. So this is the first Chern-Losik class. And yes, and now, of course, we define this class, and question is, is it possible that this class is non-trivial? So we need to find some examples, some model examples, and we try to understand what means this triviality or non-triviality of this class. And first of all, what means that class is trivial? So omega is trivial if and only if we can integrate this class, so we can find some form theta such that d theta equal omega. Theta is a one form, And what is important that theta should be invariant with respect to f tilde. So, okay, and now theta looks okay like this. So a dy1, b, c, d. So a, b, c, d are some functions. And now we use the following trick. We assume that all iterations of this diffeomorphism can be included in one parameter group of diffeomorphisms. In this case, we can average this form, so integrate, and after this averaging, this new form already doesn't depend of psi. And so we get some invariant form which satisfies this equation. So this trick allows to us suppose that theta is not invariant with respect to one diffeomorphism, but invariant with respect to some one parameter group. And this gives differential equation. So this is the main tool here. So now we have this equation. So we replace f invariance with by this differential equation, Lie derivative of theta with respect to some vector field equals 0. This vector field can be computed. So this is vector field in space of jets. And this equation that d theta equals our Chern-Losik class can be rewritten on the language of these functions. So a, b, c, d functions, they satisfy these equations. And equations can be, yes, and so these equations means that d theta equals omega, and these equations are equivalent to Lie derivative equals 0. So we need to solve this system of equation or prove that there is no smooth solution. Okay, it's okay, a huge system, but this system has very good symmetries, and in fact, it can be proved that okay, the previous equation can be resolved in this way. So we can find some function f such that theta equals to this, and this allows to simplify this system of equation. Yes, this is final simplification. So, what we have, an existence of smooth solution of equation 3 means okay. We have this equation for function g, which is equal to f minus this function. And the existence of smooth solution of this equation is equivalent to triviality of first Chern-Losik class of foliation, which is generated by f. So in fact, and okay, I think there is impossible to say something about this equation generally, and we need to consider more concrete example and investigate this example. In this case, investigate this equation. And so we consider two examples. So the first, okay, the first example. In this example, f consists of f is generated by vector field, and vector field is the following. So what we see, the field minus y2, y2 minus y1 means that we have rotation around the central point in the disk. And the f also gives some additional dependence of radius. So we have, okay, I think it's clear on this picture. So every point goes to some point on this circle, which goes through this point. And so the leaves of this foliation are following. We have central circle in the solid torus, and we have these, I don't know the right word, helices, something like helices. Sorry? Yes, around this central circle. So this is foliation on solid torus. For example, we can consider open solid torus without boundary. And okay, and what is proved in this case that for any function f, first Chern-Losik class is trivial. So this example is not so interesting in some sense. And how to investigate this question about triviality? We rewrite. Yes.
If you go back to one more slide.
One more?
Yeah. So, I mean, this form of the equation, it's kind of a transport equation for G, if V is known. So maybe I'm not following very well, but is V known in this case, or is that something you specify in advance?
Yes, we know V, yes, because V is related to vector fields which generates F. Yeah. So yes, this is the equation, differential equation of first order.
Yeah.
And so we have some standard technique with characteristics.
Right.
And
okay.
This is the main method.
Okay, so that's the main thing you're relying on. That's the main solution method that you're using.
Yes, yes.
Okay.
Okay, so we have, this is our equation in this case with vector fields. Yeah, so we explicitly see these vector fields. And in fact, for this vector field, because of this rotational symmetry, we have the full number of integrals. So this is integrals, alpha, beta, gamma, delta are some constants, and we have general solution in this form, and we can easily take R equals 0 and okay, D alpha, beta, gamma equals beta, and so we have this solution. So this is explicit solution of this equation, and this gives triviality of Chern-Losik class. Okay, so this is the first example, and the second example I would like to talk about is the following. In fact, it's okay. In this case, we also have solid torus. Again, we have this central circle as one of leaf, but now we have F, which looks like, if you consider disk, this is a fixed point, and now vector field is directed from this point to along the radial direction. But the length of this vector depends of radius. What does it mean? This means that we have circle, and from this circle we have asymptotically, how to say, so this central circle, and we have asymptotical leaves which goes from this circle to the boundary. So the asymptotics is generated by this vector field. So we see that vector field is proportional to x, and the model of this vector is defined by this function f. And also I have this picture that every vector directed along the radial direction. So, okay, this is the leaves explicitly described. And what we have, so we have exactly one compact leaf. It looks like, okay, rib foliation. And all other leaves are non-compact. And they asymptotically goes from this central circle and also asymptotically converge to boundary. So it's the geometry of this foliation. And what we have in this case, again, triviality of Chern-Losik class is equivalent to this equation. This is an equation, okay, of the same type with the vector fields. And okay, and now general theories say that we have something like this. So G is this integral plus some smooth function of y2 divided by y1. And of course, we have some different. Okay, so for example, in the point where y1 equals 0, we need to replace y1 divided by y2 divided by y1 by inverse value. And we use now the following trick. Let's remark that equations are invariant with respect to following change of coordinates. And if we make this change of coordinates, then we have the following, the new function looks like the following. So we see that this, in fact, this is a standard action on, okay, which is related to group PSL. So we see this. And let's integrate this function. So we can see the function h alpha of d and integrate with respect to alpha. So again, we use some averaging with respect to action. After this integration, this coordinate y1 divided by y2 disappears. So we have invariant coordinate here, invariant coordinate here, and we have non-invariant coordinate here. After averaging, this coordinate disappears. And so we can state that general solution G, if there exists some general solution of this form, then there exists different solution which doesn't, where function D doesn't depend of this coordinate y2 divided by y1. But if we have no this coordinate, then smoothness of this function implies smoothness of these integrals. So what we have, we get that existence of smooth solution of equation is equivalent to smoothness of this integral. And then we proved that Chern-Losik class is trivial if and only if f of 0 is not 0 and all derivatives in 0 point equals 0 for all k. So this is equivalent to smoothness of this integral. So what we see that this foliation gives an examples of foliation with non-trivial Chern-Losik, first Chern-Losik class. Okay, so I think that maybe this triviality or this non-triviality of Chern-Losik class is related to this asymptotic convergence of non-compact leaves to the compact one. So we have this convergence in the previous example. We have some these leaves which are on some distance okay, on some fixed distance from the circle in the first example. So if you consider the first example, let's look. We see that all leaves, even non-compact leaves, they situated on some fixed distance from the compact leaf. We have no asymptotic convergence at all. But here we have this asymptotic convergence to compact leaf, and maybe this is the reason why Chern-Losik class is non-trivial. Okay, so, okay, thank you. So, yes?
In the abstract of your talk, you mentioned that a generalization of Gelfand-Fuchs, yeah, cohomology theory. So that a Gelfand-Fuchs is a cohomology of vector field, right?
Yes, because there are some, yes, there is some general approach to these classes. I didn't talk about this, but if you consider, okay, because this can be done on the language on Dn spaces, yes, Dn manifolds. Yeah, so if you consider the point, and then you have maps to these points, then in fact, okay, this cohomology of S2 prime of F, in fact, is cohomology of Wn, so formal vector fields with coefficients in GL, with respect to GLN. And of course, because when these points, you can map these points, okay, you can map any space in this point, one point space, and so you have map from this to S2 of foliation. And so all characteristic classes comes from this algebra. So, and there are plenty of classes in higher dimension. So in dimension 1, we have only two classes, Godbion-Weil class and Chern-Losik class. But if you consider already dimension 2, you have many classes, and okay, and we consider only one of them, which looks like generalization of Chern-Losik. Because, okay, I said that this class generally looks like y1 in special coordinates, y2, and so on, plus yn. I described these coordinates. And but in dimension 1, omega is simply y1. This is exactly Chern-Losik class. So it's very natural generalization of Chern-Losik class. Also, I think that maybe Anton already made talk about this here, that there are in other classes which generalize Godbion-Weil classes and then other classes. So there are many classes, but okay, this is maybe the most reasonable one, which I talk about. But all they come from this Gelfand-Fuchs.
There's still a lot of work to.
Yes, but I think maybe the most important to understand what geometry stay related to this class. It's not clear, in fact.
Okay, then let us thank the speaker again.